First, we have two examples left in part C of module 2. Yeah. So let us finish those two examples first about asymptotic notations. Yeah. So let's look at our first example. Example 2.3. Yeah. Show that this cubic function, parenthesis n plus 2 cube, belongs to big theta of n cube. So for this question, we can use two methods to prove it. The first one is a simple one, because this big theta notation, we have a special way using the limit. Remember, the limit way, when the ratio of two growth functions equals non-constant c, that case corresponds to the big theta case. First, let's do it in that way. The second way, just the definition way. Actually, the definition way is much harder than the limit way, but here we want to understand the definition better, so we practice that definition way after that limit way. Okay? All right. Yeah. So let's look at the first way quickly. Yeah. First way, we just calculate the ratio. F function, that is n plus 2 cube, and the g function, that's the n cube. Yeah. All right. Then we have for the question like this, we have some special transformation way to make it easier to calculate the limit. Yeah. So usually we can write in this way. Yeah, the limit. Then, so let me write. So can you see it equals, here, the numerator is 2 cube. Yeah. Because the numerator has that 3 at exponent. Denominator also has that 3 at exponent. So let us take that 3 exponent number out of the whole parenthesis. Yeah. Inside the parenthesis, we have n plus 2 over n, but that n plus 2 over n we can further simplify to these two terms. The first one is 1, because n over n, that's 1. Second term, 2 over n. Yeah. Then, when we work on this form, then it's much easier. Yeah. Because that cube, so we can, ignore the cube. We can take the limit directly inside the parenthesis. Yeah. So that is one of the properties of limits. Yeah. If you consider the limit inside that parenthesis, one constant part, so still the same constant, 1. Second term, 2 over n. When n goes to infinity, 2 over n goes to 0. So 1 plus 0 is still 1. So after you get the limit inside the parenthesis, that is 1. Then you take the cube after it. 1 cube, still 1. Yeah. So we get 1. Yeah. 1 is a non-zero constant, right? Yeah. So actually, it's a positive constant. Then we know if the limit of the ratio of two growth functions equals a positive constant, we know the numerator function belongs to the big theta of the denominator function. Okay? Yeah, so that's the, first proof. Yeah. But here, let us use the definition of the big theta to do another different proof without using the limit method. Yeah. All right, I hope you still remember the definition of the big theta asymptotic notation. Yeah. So actually, you need to find upper bound and the lower bound, right? C1, C2. Yeah. All right, so here, let us do that work. Yeah. So we place f function right here. Yeah. Next, we need to find two bounds. The lower bound as a multiple of g function, g, n cubed. Second, the upper bound as a multiple of that g function. Yeah. Which one is easier? When we work on this question with two cases, lower bound case, upper bound case, we always start with the easier case. That's the lower bound, right? Lower bound case much easier. Yeah. So you can see m plus 2 is greater than n, right? And we also know this n is a non-negative number. Yeah. So in that way, so we only compare some two non-negative numbers, then raise to cube operation. Yeah. In that way, here, when I do some algebraic operation here, I emphasize the number is non-negative. Okay, yeah, because if we have negative numbers, when we raise negative number to certain power, then we need to be careful. Okay, yeah. So here we don't have that problem. So yeah. All right. Then we can see when n greater or equal to 0, this inequality always true. Yeah. So we have a lower bound. And we have the coefficient for this lower bound function, that is 1. So we found C2 equals 1. That, our first constant. Yeah. After that, then we move to the upper bound. When we move to the upper bound, yeah, this time, how do we do it? Yeah. Yeah. Here, because the way you choose to do it is important. Yeah. If you choose the wrong way, then you need to do a lot of work and the proof could be very messy. Yeah. So here we want to choose a simplest way. Yeah. All right. So there is a power here, right? Power here. Yeah. But when we work on question like this, yeah, power of certain number, the base number, yeah. So we should work on the base number first. Let's forget about the exponent. Yeah. So let's just do the upper bound inequality on the base part. Yeah. Because in that way, it's much easier. Yeah. All right. n plus 2. Can we find some upper bound for this n plus 2 function? Yeah. We did that before, right? So if you recall our first example, 2.1. Yeah. So we did that. Okay. n plus 2, we can use some constant multiple of n to bound it. Yeah. So that is, we replace 2 by n, but we like the n plus n greater or equal to n plus 2, so we need to put a condition. the condition is n greater or equal to 2. Yeah. So we have some, yes. So here, we can add some condition there, right? Yeah, because otherwise, so you worry about, how about when n less than 2, right? Yeah, so then, you can not get an upper bound. Yeah. Fortunately, remember, in our definition, we can choose some special n0, right? Yeah. So this extra condition just corresponds to the choice of n0. Yeah. So we have that freedom. Remember, we have some freedom to choose that n0 constant. Now, here we use that freedom. Yeah. After that, then we raise the base numbers, both sides, to third power. Okay, third, both sides. So we get, the f function less than or equal to 8 times n cubed. Yeah. So that is our C1 constant, right? The 8 is our C1 constant. Yeah. After that, then, we found 3 constants, C1, C2, and N0. Yeah. So when we apply the definition method, if you get these 3 constants, then you're done. Okay? So then you're done. Yeah. All right. Yeah. Before we move to the next question, I want to make some comments. Yeah. Because when I assigned similar question of this one to my previous students before, I noticed some big problem. So here I like to mention, yeah, because many students, when they solved this problem, the first thing, they expand this polynomial. Yeah, so expand it, yeah, because they feel, in their mind, they feel more comfortable working on the expansion of this polynomial. Yeah. All right? Yeah. So for this one, the expansion is like this, because they can apply this formula, right? Yeah. So n cubed plus 3 to 6n squared plus 12n plus 8. So they expand our f function in this standard form. Yeah, we can call it the standard form of the polynomial. But after that, if you work on the lower bound, that's easy, right? Yeah, because the first term, yeah, so you can write greater than. That's easy. But when you work on the upper bound, then it is quite messy, right? Yeah, because you need to estimate other terms, yeah, other than the first term, then how to estimate the second term, how to estimate third term, and the fourth term. All right? Yeah. Although, eventually, you can handle it, yeah, yeah, because it's not too complicated. Eventually, they can handle it, yeah, yeah. But it is very messy. Okay, it is very messy. Yeah. So here, my comment. So I want to let you know this is a bad method. Yeah. So you make the thing more complicated. Okay. Yeah. Because if you have this kind of understanding, when you move to the higher power, higher, okay? All right. If you work on n plus 2 to the 5th power, do you still want to do the expansion? Or even higher power, you still want to do expansion, right? So you will see that direction is very bad, right? So that direction, yeah, very bad. Yeah. All right, so that's my comments for our first example today. Let's work on the second example. Yeah. 2.4. Yeah. Show that log of n belongs to little of n. Yeah. So little o, so we only use the limit way. Okay, yeah, limit way. Yeah. All right. And here I didn't specify the log base. Yeah. So in our computer science context, yeah, our default log base is 2. Default log base. Yeah. Yeah, because usually we use the binary system, right? So when we do analysis, most of the time we use the base 2, the binary system. Yeah. Yeah. In math, it's different. In math, people rarely use the binary system. Yeah. So most of the time, people use the decimal system. Yeah. So the default log base in math, that's 10. Yeah. Yeah. But sometimes people also can use the general log base, a. Okay? So with a greater than 1. Yeah. So that's more general. Yeah. All right. So here we may use that a version. Yeah. Yeah. But 2 version also fine. Okay. All right. So let us use that limit method. For the limit method, yeah, still the discrete variable problem, we need to switch it to the continuous variable version. Yeah. So let's jump to the continuous version of the function, the ratio of log of x over x when x goes to infinity. Yeah. Here, because x is a continuous variable, so we can take derivatives on numerator and the denominator. Yeah. Before we apply the L'Hopital's rule, yeah, so here you can see we're going to apply L'Hopital's rule. Before we apply the L'Hopital's rule, yeah, check the condition. The condition is infinity over infinity indeterminate form. So we are safe. Otherwise, you may do in some wrong way, right? So if you forget to check the condition, so you may do it in the wrong way. Yeah. All right, so here, so let's apply the L'Hopital's rule. Yeah. So we take the limit, then we take derivative of the numerator. Yeah. So we copy the formula. Yeah. So that is 1 over natural log of a times x. Yeah. So the natural log of a, because a greater than 1, so it is a positive number. Yeah. But it's a constant. Yeah. All right. The denominator, its derivative equals 1. So after simplification, the limit we want to calculate. Yeah. So we get 1 over natural log of n times x. Yeah. But this new form, yeah, so I hope you do not apply the L'Hopital's rule directly, yeah, because sometimes people just like a machine, right? Without thinking, yeah, you just do something, naturally, so based on your intuition, yeah, so without thinking, yeah, but here, this is not infinity over infinity indeterminate form, because the numerator is a fixed constant number 1. It is determinate, right? Yeah. So denominator goes to infinity. So 1 over infinity. So you get the answer immediately. That's 0. All right. So the limit of this continuous version is 0. So at the end, we need to go back to the discrete version. Excuse me. Discrete version. Yeah. So this version tells us equals infinity. Yeah. So then, our conclusion, because that's the meaning of little o. Excuse me. Yeah. So then we solve this problem completely in this way. Yeah. Just another review. Okay. All right. Yeah. So that's the last 2 examples in part C. Next, we have 3 more examples.